Welcome to the next video in the series on condensed matter theory. In this lecture I want to talk about plasmons. In the previous video we have seen that for frequencies smaller than the plasma frequency, metals reflect, and for frequencies larger than the plasma frequencies, metals become transparent. And we can think of this when your frequency of your light is small. The electrons inside your metal start to oscillate with the frequency of the driving force. Thereby they generate a screening field, and that field inside the metal will screen the electrical field of the light. Therefore the total field is exponentially decaying. The light cannot penetrate into the metal and is reflected. And that happens for omega smaller than omega plasma. We have reflectivity, reflection. When the frequency of the light is larger than your plasma frequency, the electrons inside cannot keep up with that oscillation and your metal becomes transparent. Now the plasma frequency is related to an internal resonance. And in order to show this, we can assume that we have a charge density wave with a resonance at plasma frequency, and then show that this is a consistent solution or a consistent assumption with the Maxwell's equations that describe the interactions between the electrons and the fields and the forces. So we assume that for the resonance we have our charge density, which normally is just a constant, but now we can add an excitation on that, where the charge density starts to oscillate with a frequency and a wave factor. So the charge density is no longer homogeneous but has an oscillation on top of that. And this oscillation has frequency omega and wave factor k. Now in order to show that this solution is in agreement with the Maxwell equations, we can have a look at the continuity equation that states that the derivative of J is equal to the time derivative of the density. So when you locally change your charge density, that can only happen because there is a current in or out of that position. And we know that our current density is given by Ohm's law as the conductivity tensor times the electrical field. So now we take the derivative, and we find that sigma derivative of E is, and here we take the derivative of our assumed field, and we just get an I omega in front. I omega rho. And the minus sign takes that minus sign away. Now we can use that we know what the derivative of an electrical field is, which is namely the charge density. So we have 1 over epsilon 0 sigma density must be equal to I omega times the density. This equation has a solution if sigma divided by epsilon 0 I omega is equal to 1, or when 1 plus I sigma divided by epsilon 0 omega is equal to 0. And what we have here on the left is exactly our dielectrical constant, epsilon of omega, which has to be 0. So we find that whenever epsilon of omega is 0, which is exactly the boundary where the plasma frequency becomes larger or smaller than 0, we have a solution for a charge density wave in our material. So that's the resonance that you have at the plasma frequency. We can understand this plasma frequency even in more microscopic detail if you think of your ions that sit in your sample. Then we can move the electrons and we can shift them by a distance d. And we can now write down an equation of motion for the distance d and see what the resonance frequency of this oscillation would be. And when we have this situation, we have a surface charge. Which is plus minus n d mal e times e. So charge density times the distance times the electric charge, and the field induced. That's the surface charge per area. And the field that we get in a condensator is then given by NdE over epsilon 0. So our equation of motion, F times mLA, the mass times the second derivative of D is minus the electric charge times the field. And of course we can now put in the electrical field as NdE over epsilon 0 is minus 1 over epsilon 0 NdE square. So the resonance frequency is 1 over epsilon 0 NE square over m, or the square root of that. So the resonance frequency that we find is square root of NE square over epsilon 0 m. We can put in the sigma 0, epsilon 0, tau, and that is exactly the plasma frequency that we had before. So we see that the electrons can basically slosh back and forward in your solid at the frequency, the plasma frequency, and that is exactly the resonance frequency where you go from a reflective material when the frequency is smaller to a transparent material when the frequency of the light is larger. So with that we've seen that metals turn from being reflective to being transparent at a certain frequency, and that happens at the resonant frequency where the electrons are able to oscillate back and forward. And of course in the example here I assumed that the wavelength of that wave is much longer than the size of your sample. If that wavelength is shorter, you will find that you have a density wave inside your sample, as we discussed before. Very good. In the next video I want to talk about the specific heat. We have now seen several cases where the Drude model and classical interpretations were able to describe material properties. Of course, that's not always true. And in the next, that's almost never true. In the next video, we will show you the specific heat and show you a case where this fails. And it also fails in a way that really shows you the importance of quantum mechanics. So the experimental result of the specific heat that you find in metals is rather counterintuitive if you assume a classical world. Or is basically you can't explain this with classical physics. And there the boundaries of the Drude model really show nicely. But that's for the next video. Thank you very much for your attention. We see each other next time. Stay healthy.